Hello children, let us understand how to represent a complex number in different forms. A complex number can be represented in four different forms, and they are geometrical representation, polar representation, exponential representation, and vectorial representation. We will understand them one by one. First one, geometrical representation. We have already seen this. Horizontal line is called as real axis, vertical line is called as imaginary axis. They intersect at origin. Suppose there is a point P represented by ordered pair x, y. This is x and this is y. So complex number it represents is z is equal to x plus iy. Its conjugate is x minus iy. Its modulus is under root x square plus y square. Its argument theta is equal to tan inverse y by x. This plane is called as complex plane, Argand plane, or Gaussian plane. Second one, polar representation. In this figure, OQ is equal to x, also mod z cos theta, and PQ is equal to y, also mod z sin theta. So complex number z is equal to x plus iy can be written as mod z cos theta plus mod z sin theta into I. Take mod z common in both the terms. So it will be mod z into cos theta plus I sin theta. Write r in place of mod z. So z is equal to r cos theta plus I sin theta, where r is equal to mod z and theta is argument of z. This is called as polar form. If we use general value of theta, then polar form can be written as z is equal to r cos 2n pi plus theta plus I sin 2n pi plus theta, where r is equal to mod z, theta is argument of z, and n is integer. Third one, exponential representation. Suppose z be a complex number such that mod z is equal to r and argument of z is equal to theta. Then z is equal to r e to power I theta is called as exponential form. Here e to power I theta is equal to cos theta plus I sin theta. This is known as Euler's formula. Also, cos theta is equal to e to power I theta plus e to power minus I theta upon 2. And sin theta is equal to e to power I theta minus e to power minus I theta upon 2i. These two are known as Euler's identities. Fourth one, vectorial representation. Suppose P is a point in complex plane that represents complex number z. So z can be represented by vector OP. Mod of vector OP is equal to mod z. Now let us see few questions based on representation of complex numbers. First question, express 1 plus 3i upon 1 minus 2i in polar and exponential form. Suppose z is equal to 1 plus 3i upon 1 minus 2i. First we will write z in standard form, that is z is equal to a plus ib. To do that, we will multiply both numerator and denominator with conjugate of denominator. Conjugate of denominator is 1 plus 2i. So we will multiply numerator and denominator with 1 plus 2i. So it comes out to be equal to minus 1 plus I. So mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to under root 2. To calculate argument of z, we will first calculate alpha such that tan alpha is equal to mod of imaginary z upon real z. That is equal to mod of 1 upon minus 1. Mod is always positive. So tan alpha is equal to 1 or alpha is equal to pi by 4. Here real part of z is negative and imaginary part of z is positive. So z is in second quadrant. That means theta is equal to pi minus alpha. We have calculated alpha as pi by 4. So theta is equal to 3 pi by 4. In polar form, z is equal to r cos theta plus I sin theta, where r is equal to mod z and theta is argument of z. So r is equal to under root 2 and theta is equal to 3 pi by 4. So z is equal to root 2 cos 3 pi by 4 plus I sin 3 pi by 4. In exponential form, z is equal to r e to power I theta. R is equal to root 2 and theta is equal to 3 pi by 4. So z is equal to root 2 e to power I 3 pi by 4. Second question, what is the locus of z if amplitude of z minus 2 minus 3i is pi by 4. When we are dealing with coordinate geometry, we should assume z is equal to x plus iy in place of a plus ib. So z minus 2 minus 3i is equal to x plus iy minus 2 minus 3i. It is x minus 2 plus I into y minus 3. This is in standard form. Amplitude of z minus 2 minus 3i is equal to amplitude of this. Amplitude of z minus 2 minus 3i is given as pi by 4. Amplitude of this is equal to tan inverse imaginary part upon real part, or tan inverse y minus 3 upon x minus 2. So it is tan pi by 4 is equal to y minus 3 upon x minus 2. Value of tan pi by 4 is equal to 1. So 1 is equal to y minus 3 upon x minus 2. It can be simplified as x minus y plus 1 is equal to 0. This is equation of straight line in the form ax plus by plus c is equal to 0. So locus of z is a straight line. Third question, if a complex numbers z1 and z2, argument of z1 minus argument of z2 is equal to 0, then show that mod z1 minus z2 is equal to mod of mod z1 minus mod z2. Suppose z1 is equal to r1 into cos theta 1 plus I sin theta 1 and z2 is equal to r2 into cos theta 2 plus I sin theta 2 in polar form. It is given that argument of z1 minus argument of z2 is equal to 0. So argument of z1 is equal to argument of z2. Suppose argument of z1 is equal to theta 1 and argument of z2 is equal to theta 2. So theta 1 is equal to theta 2. Let's say it is theta. Mod z1 is equal to r1 and mod z2 is equal to r2. z1 minus z2 is equal to r1 into cos theta plus I sin theta minus r2 into cos theta plus I sin theta. We can take cos theta plus I sin theta common in both the terms. So it will be r1 minus r2 into cos theta plus I sin theta. So mod z1 minus z2 is equal to under root r1 minus r2 whole square into cos square theta plus sin square theta. Value of cos square theta plus sin square theta is equal to 1. So mod z1 minus z2 is equal to under root r1 minus r2 whole square. Now we can square both the sides. So it will be mod z1 minus z2 whole square is equal to r1 minus r2 whole square. Again we can take square root of both the sides. So mod z1 minus z2 is equal to mod r1 minus r2. r1 is equal to mod z1 and r2 is equal to mod z2. So mod z1 minus z2 is equal to mod of mod z1 minus mod z2, which we had to prove. Fourth question, if xn is equal to cos pi by 2 to power n plus I sin pi by 2 to power n, prove that x1, x2, x3 and so on up to x infinity is equal to minus 1. Suppose z1 and z2 are two complex numbers. They can be written in polar form as z1 is equal to r1 into cos theta 1 plus I sin theta 1 and z2 is equal to r2 into cos theta 2 plus I sin theta 2. z1 z2 is equal to r1 r2 into cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. It can be simplified as r1 r2 into cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 plus I into sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. We know that this can be written as cos theta 1 plus theta 2 and this can be written as sin theta 1 plus theta 2. So z1 z2 is equal to r1 r2 into cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Point to be noted here is when two complex numbers in polar form are multiplied, their magnitudes are multiplied and their arguments are added up in cos and sin functions. We can extend this result to n number of complex numbers. So we can say in this case x1, x2, x3 and so on up to xn is equal to r1, r2, r3 and so on up to rn into cos pi by 2 plus pi by 2 square plus pi by 2 cube plus and so on pi by 2 to power n plus I sin pi by 2 plus pi by 2 square plus pi by 2 cube plus and so on pi by 2 to power n. Here we are putting the values n is equal to 1, 2, 3 and so on up to n. This is GP series whose sum is given as S is equal to A into 1 minus R to power n upon 1 minus R, where A is first term, R is common ratio, and is the number of terms. First term is pi by 2, common ratio is 1 by 2, and number of terms are n. So S is equal to pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2. We will study this in sequences and series chapter. Here R1, R2, R3, Rn are all equal to 1. So x1, x2, x3 up to xn is equal to cos pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2 plus I sin pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2. This can be simplified as cos pi into 1 minus 1 by 2 to power n plus I sin pi into 1 minus 1 by 2 to power n. We have to get the value of infinity terms multiplied together. So we will take limit n tends to infinity on both the sides. So it will be x1, x2, x3 and so on up to x infinity is equal to cos pi into 1 minus 1 by 2 to power infinity will be equal to infinity. So 1 minus 1 by infinity plus I sin pi into 1 minus 1 by infinity. 1 by infinity is equal to 0. So it can be simplified as cos pi plus I sin pi. Value of cos pi is equal to minus 1 and sin pi as 0. So the result is minus 1, which we had to prove. In next video, we will see rotation theorem, the Myers theorem and cube root of unity. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.